Okay, good afternoon, everybody. My name's Susan Lawrence, and you're here at our TESS seminar. Before we begin, I'd like to acknowledge the traditional owners of the lands on which JCU is here today, the Japagai, Gimoy, Walubara, Yidinji, and Iriganji people, and to pay my respects to their elders past, present, and emerging. So it's with great pleasure that I introduce our speaker today, Professor Ian Lowe. Professor Lowe is an emeritus professor at the School of Environment and Science at Griffith University. He was formerly educated as a physicist at the University of York, and he's a doctor, both a PhD in physics, but also a Doctor of Science based on his field, his research production. Professor Lowe's research is focused on energy supply and use, particularly the environmental consequences of climate change and the broader issues of population growth, as well as sustainable futures. He's published widely and among his many advisory roles, he's represented the public interest on the Radiation Health and Safety Advisory Council for 14 years, was a member of the expert panel advising South Australian Nuclear Royal Commission, and a fellow of the Australian Academy of Technology and Engineering, where he reviewed a recent report on small modular reactors. So if you please welcome Professor Lowe. Perhaps you should start with the green hat.
Yes, the green hat is that I finally achieved something significant 12 years ago when I was in the first Australian over 70s cricket team to tour England. Just shows you've just got to hang in there, and eventually your contribution will be honoured. I'd also like to acknowledge the traditional owners and pay my respects to their elders, past, present, and emerging. That's not an integral part of whitefellow tradition, but I have to say the idea appeals to me as I totter unsteadily into that category myself. This is Alan Moyer's view of our debt to the original Australians. And I've said to people that acknowledging them has become a bit of a ritual, but it should be more than a ritual, because they worked out over tens of thousands of years how to live within the limits of the natural systems of this harsh and unforgiving continent. And they embodied those knowings not just in custom and practice, song and dance and ceremony, but in their system of laws. They actually had a system of laws that enabled them to live sustainably. And we, in principle, are committed to the idea of developing sustainably. COAG in 1992 adopted the National Strategy for Ecologically Sustainable Development. But you'd have to say you'd search very diligently in the utterances of those aspiring to lead us after the 3rd of May without seeing much evidence that they even know we have a national strategy for ecologically sustainable development, let alone seeing that as the framework within which we should be operating. Question is, can small modular reactors help us reduce greenhouse gas emissions? I'm tempted to say the answer is no. Are there any questions? But that might seem a bit glib. But I share this other view of Moyer, which has Peter Dutton flogging a very dead radioactive horse. I'm going to say a bit about the general issue of Australia's role in the nuclear industry, and then focus in on the question of small modular reactors. And if you want to know more about them, I refer you to the report by the Academy of Technology and Engineering, imaginatively titled Small Modular Reactors. I was one of the reviewers of that report, and I'm drawing on it in what I'm going to say. Let me remind you of the history. 100 years ago, we didn't really know anything about the nucleus. And the basic physics was worked out in the 1930s. That led to the Manhattan Project and the first nuclear weapons, which ended World War II. After the war, the Americans were characteristically unhelpful and decided they didn't want to share their technology with the Allies who'd contributed to the Manhattan Project. And so the British built a reactor at Calder Hall to produce their own plutonium for their independent nuclear weapons. as a public relations gimmick at the last minute, they decided that they could use the heat of the nuclear reaction, which was producing plutonium, to boil water and provide electricity to about 100 houses. And they persuaded the new young Queen Elizabeth II to turn a switch, thus giving the public the impression that Calder Hall was built to supply clean nuclear electricity. In fact, Calder Hall was built to provide plutonium for the British bomb, and the electricity was a spin-off. But the public relations benefit of showing that the nuclear reaction could produce energy was not lost on the Americans. Under Eisenhower, he proclaimed an Atoms for Peace project, and they supplemented the reactors which they had built to produce plutonium for more bombs with reactors which were purposely designed just to boil water to produce clean electricity. My personal journey, I grew up in the east of Australia and regularly heard of people being killed and injured in coal mines, and I saw the pollution of air and water from burning it. And I studied electrical engineering and physics, and I was quite attracted to the idea of using the nuclear reaction to provide cleaner electricity than we were getting from burning coal. And I had no problem at all going to the University of York, accepting a scholarship from the UK Atomic Energy Authority to study the basic physics of a problem that affects the useful life of fuel elements in nuclear reactors. I won't bore you by talking about non-equilibrium diffusion in ionic solids. But my first academic job was at the UK Open University. And the Open University was started by the Wilson Labor government to provide a university education as a second chance for people who missed out on university after leaving school in the UK. And because only about half as many as a percentage of school leavers who went to university in Australia went to university in the UK, there was a huge pent-up demand of people who were capable of university education, but through the lottery of places at the end of leaving school didn't get it. So I got an academic job in the UK Open University. The Wilson government lost the 1970 election. They were replaced by the Heath government, and Margaret Thatcher was the education minister, and she thought the idea of an open university was socialist nonsense, that if people were good enough to get to university as she was, then they got an education, and those who didn't get an education didn't deserve it. They couldn't stop the university operating because they had already offered places in the first year to 25,000 taxpayers, but they could slow down the capital funding, and they did. So for the first 6 years I was working there, like the others in the faculties of science and technology, we were working in wimpy huts, the sort of temporary huts that are used for workers on building sites. That meant that we couldn't do the sort of research that we had been doing before we got appointed. And a group of us started doing pencil and paper research about energy. Then the OPEC oil crisis happened and energy was suddenly flavour of the month. And I never went back to maltreating atoms. We were involved in a major project because there was a big debate going on in the UK in the 1970s about whether the next generation of power stations should be coal-fired or nuclear. When we went to the literature, there were papers in the refereed literature showing that nuclear electricity was cheaper than coal. There were also papers in the refereed literature showing that coal-fired electricity was cheaper than nuclear. How could that be? Well, the answer is that there isn't an agreed methodology for comparing the costs and revenues over an extended period, 10 years of building a power station, 30 years of operating it. Everyone agrees that a nuclear power station has a higher capital cost than coal because the nuclear reaction is a much more complicated way of boiling water than burning coal. But the running costs are much lower because you don't need to supply 5 million tonnes of coal every year. So since there are different agreed methodologies for comparing capital costs with running costs over 30 years, understandably, people with an axe to grind choose the assumptions that give the sort of answer they want. You probably know the old joke of an interview panel that at the end of the standard interviews asked the candidates, what's 1 + 1? And the first candidate was an engineer who looked puzzled and said 2. The second candidate was a mathematician who said, well, actually, 1 isn't 1. 1 is something between 0.5 and 1.5. So 1 + 1 could be anywhere between 1 and 3. I need more information. They thanked her. The third candidate was a resource economist and asked what 1 + 1 would be, looked shifty and said, "What do you want it to be?" The point is, you can choose assumptions for discount rate, for future fuel costs to give the answer that you want. It was also, at the time, proposed by the British Atomic Energy Agency that Britain should build a crash program of building 36 nuclear reactors to avert the coming energy crisis. Now, we in the Energy Research Group hadn't noticed a coming energy crisis. So we did some calculations, and what we found is that if the UK had built 36 nuclear power stations in 10 years, there would have been an energy crisis caused by the amount of energy needed to build and fuel 36 nuclear power stations. And the industry would then have been able to say, well, just as well we built the power stations because we have an energy crisis. The point is that although the media release by the coalition announcing their plan to build nuclear power stations uses the phrase zero emissions nuclear no fewer than 11 times in 2¼ pages, it is just nonsense to talk about zero emissions because of the huge amounts of conventional materials that are needed to build and fuel a nuclear power station. I was back in Australia when the Fox report about the Ranger uranium mine was published, and the Fox report said that operating the Ranger uranium mine would probably be profitable, but would not have any significant overall economic impact, and the community should decide whether we wanted to mine and export uranium, taking into account the observable fact that nuclear reactors inevitably produce radioactive waste that has to be managed for geological time, and there is a risk of fissile material being misused for weapons. And after I came back to Australia, I was involved in the National Energy Research Council, the Radiation Health and Safety Advisory Council, and the South Australian Royal Commission. If you look at nuclear energy in Australia, basically we haven't used nuclear energy. We supplied uranium to the UK and the USA, initially for their weapons and then later for their power stations. In the 1960s, there was a brisk debate in all of the eastern mainland states about whether we should use nuclear power. And where it always came unstuck was that we didn't have a national grid. Each state had its own separate electricity system, and no state had an electricity system that was large enough to justify the smallest nuclear power station that looked economically feasible, because there really are economies of scale. It doesn't cost 4 times as much to make a 2,000 megawatt power station as a 500 megawatt one. So the smallest unit that looked economically feasible was too large for the New South Wales grid or the Queensland grid. Finally, those advocating nuclear power, led by the late Sir Philip Baxter and Sir Ernest Titterton, persuaded the short-lived Gorton government, after Harold Holt went for a one-way swim at Portsea, to build a nuclear power station on Commonwealth land at Jervis Bay, get around the fact that none of the states were going to do it. And the Commonwealth government went as far as calling tenders for the construction of a nuclear power station at Jervis Bay. By the time the tenders came back, there'd been another internal coup in the Liberal Party. Gorton had been displaced by Billy McMahon, and Billy McMahon, for all his manifest failings, could read joined up writing and do takeaway sums, and he was alarmed that the cost was about double what they had been assured it would be for a nuclear power station. So he put the project on hold, and then the Whitlam government was elected and they closed it down completely. So after 1972, there had been no serious proposals to use nuclear power in Australia. We had 2 large uranium mines at Ranger and Olympic Dam in South Australia. In 2006, John Howard finally found it a political embarrassment that he'd done nothing about climate change, and he appointed Dr. Ziggy Switkowski, who headed the Australian Nuclear Science and Technology Organisation, to conduct a review. John Clark called it an independent group who all want nuclear power by Tuesday. And they toured the world trying to make as good a case as they could for Australia adopting nuclear power. but you can only stretch the facts so far. What their report said was that it would require both a carbon price and other forms of government subsidy to make nuclear electricity look cost effective in Australia. And it would take at least 10 years and probably 15 to build one nuclear power station. South Australia held a royal commission into the nuclear industry. It also concluded that nuclear power was not cost effective. Interestingly, they said that South Australia could set up an economic opportunity by offering to take in radioactive waste from other countries in the region. The fundamental point is that while no one has yet built and operated a repository for the high-level radioactive waste from nuclear power stations, the general agreement is that the only safe thing to do is to store it deep underground in stable geological strata. And Finland is well advanced to engineering such a place. In the UK and the US, they still have the problem that every time they identify a site, the local people say they don't want it. But the opportunity that the South Australian government identified was that there are countries in our region that have nuclear power stations, most obviously Japan and South Korea, which do not have stable geological strata. So they argued there was a potential economic opportunity to set up shop to store radioactive waste. They put it to a citizens' jury who rejected it. And since then, we heard nothing about nuclear power until Mr. Dutton's announcement in May last year. Going back 15 years, I thought there was a legitimate argument whether in trying to slow down climate change, we should decarbonise by using renewables like solar and wind or by using nuclear electricity. And a small publisher in Sydney called Pantera Press persuaded myself and Professor Barry Brook, who was at the University of Adelaide, to cooperate to write what they called a flip book. It doesn't have a back cover, it has two front covers. So one front cover says nuclear power, yes. And if you open it there, you get Barry Brook's essay saying why Australia should build nuclear power stations and the critique that I wrote. You turn it the other side, the other front cover says nuclear power, no. And if you open it from that side, you get my essay saying why I don't think we should build nuclear power stations, followed by Barry's critique. After we published it, we did a few double acts at writers' festivals and ideas festivals. And one of them, a thoughtful member of the public said, how can two intelligent and well-informed scientists come to such different conclusions? And I said, well, we both agree that climate change is a serious issue. We both agree that we need to reduce the amount of carbon dioxide we're putting into the atmosphere. That means the only realistic options to close down coal-fired electricity are renewables like solar and wind or nuclear. Barry Brook was optimistic that we could build a new generation of nuclear reactors, so-called generation 4 reactors and small modular reactors, which would not have the problems of the existing ones. And by contrast, he was pessimistic about the possibility of scaling up solar and wind and bringing the price down so that they were competitive. And by comparison, I said that I'd been hearing tales of a new generation of reactors for 50 years. And just because someone's been consistently wrong for 50 years doesn't mean they'll always be wrong, but it doesn't mean you should accept their assurances without at least a grain of salt. And by contrast, I said, all the indications are that the research that we were funding through the National Energy Research Council when I was on it was leading to more efficient and cheaper solar panels. So I was confident that we could scale up renewables. That was the basis of our disagreement 15 years ago. And I have to say, history has been much kinder to my argument than to Barry's, because we're still waiting for the promised generation 4 reactors and the small modular reactors, about which I'll talk in a minute. This is the rapid change. When we wrote that book 15 years ago, these were the world average prices. Solar 3.35 cents a kilowatt hour, wind 14, nuclear 12, coal 11, gas 8. In 2020, world average prices, solar 3.7 cents a kilowatt hour, wind 4.1, nuclear 16. So it's not just a bit more expensive, it is much more expensive. Now, to be fair, solar and wind need storage to provide round-the-clock energy. And storage approximately doubles the cost, enough storage to be what the industry calls firm capacity. But the world has been shifting rapidly away from nuclear and into renewables. I've given you there, 2015 was the first year in which the installation of renewables was equal with fossil fuels. In 2020, 190 gigawatts of renewables and 3 of nuclear. Last year, the world commissioned 660 gigawatts of renewables, solar, wind, hydro and biomass, and a net 4.3 of nuclear. So it's clear that the world electricity industry is certainly not stampeding towards nuclear power. In fact, old nuclear power stations that have amortized their capital cost are being closed down in the Northern Hemisphere because just the cost of maintenance and operations means they can't compete with new solar and wind. And those are average figures. The lowest I could find was a new solar farm in Portugal that's producing electricity at 1.1 cents a kilowatt hour. Now, this is the latest Australian study. Every year CSIRO does a study with the Australian Energy Market Operator called GenCost. They look at the cost of wind and solar panels with enough storage to be firm capacity. It's a bit cheaper than solar thermal, significantly cheaper than baseload gas. And they've also added on what it would add to the price of gas or coal if carbon capture and storage could be made to work. Now, in fairness, after a couple of decades of research, the only thing that's been successfully captured and stored is public money. But there are still people in the industry who believe that if you throw enough money at it, it'll be possible to capture and store some of the carbon dioxide from some of the power stations. I think it's a delusion to think that it could be applied universally, because what a back of the envelope sum shows is that if you were able to capture and liquefy all of the carbon dioxide from all of the world's coal-fired power stations, you would be dealing with a volume of liquid comparable with the entire oil industry, and dealing with that from scratch, with no infrastructure. I think there may well be niche applications where there happens to be suitable geological strata near a small power station and that carbon dioxide be captured and stored. But it's a delusion to think that it can be applied universally. CSIRO's figures for large nuclear are about double the cost of wind and photovoltaic with firming. Mr. Dutton said those figures have been criticised as being unrealistic, and indeed they have by people like me, because what I've pointed out is that CSIRO has taken at face value the estimates by the nuclear industry of what a new power station would cost. But every power station that's been built in Western Europe or North America this century has been over budget by at least a factor of 2, and some by factors of 3 or 4. No one this century has built a nuclear power station in the Western world in less than 15 years, and no one has built it at less than double the original budgeted cost. And finally, they have an estimate of the costs from small modular reactors, about which I'll say more in a moment. They said as a footnote, the inclusion of nuclear is only as a point of interest rather than a practicality, because CSIRO don't believe that anybody in the electricity industry seriously wants to build nuclear power stations. Mr. Dutton's announcement last May that a coalition government would build nuclear reactors at 7 sites in New South Wales, Queensland, Victoria, South Australia and Western Australia. The Commonwealth Government would build and operate these reactors. And I have to say, I had to have a bit of a giggle at a government that proved incapable of building such complex structures as railway station car parks suddenly has the competence to build and operate nuclear power stations, but I digress. The first reactors would be operating by 2035 if they were small modular reactors, or 2037 if they were large reactors, and this would produce cheap, clean, zero emissions baseload power, a verbatim quote. And it says, and this is again a direct quote, there are 32 countries operating zero emissions nuclear plants. Of course, that means there are 160 countries that don't use nuclear power. Another 50 countries are looking to do so. I've looked in vain for evidence of that. Even the World Nuclear Association doesn't think there are more than half a dozen countries that are seriously considering nuclear power. The biggest barefaced lie, of the world's 20 largest economies, Australia is the only one not using nuclear energy or moving towards it. Well, there are 2 of the 10 largest economies, Germany and Italy, that are not using nuclear power, and another 4 in the next 10, Australia, Indonesia, Saudi Arabia, and Turkey. And the only one that could be said to moving towards it is Turkey, which is building one nuclear power station, about which its neighbours are very suspicious, but that's another story. The World Nuclear Report, this is the voice of the industry. 35 reactor constructions have begun since 2019, all by Chinese or Russian government-controlled companies. Nowhere in the world is the private sector building a nuclear power station at this moment. If you look at what's happened in the last 20 years, there are now 49 more nuclear power stations in China than there were 20 years ago, and there are 51 fewer nuclear power stations in the rest of the world. So the massive construction in China has just balanced out the closures in the rest of the industrial world. And as I said, there are 6 G20 countries that don't operate nuclear power stations. What are the obvious problems with the proposal? Well, there are so many and so fundamental that it's difficult to believe that anyone is taking it seriously. The first is it's illegal. Section 140A of the Environmental Protection and Biodiversity Conservation Act, legislated in 1999 by the Howard government, prohibits the building and operating of nuclear power stations anywhere in Australia. And Queensland, New South Wales and Victoria all have state legislation that prohibits some or all of the steps that would be needed to build and operate a nuclear power station. Second problem is technical. They say that they could have a nuclear power station operating by 2035 if it was a small modular reactor, or 2037 if it were a large nuclear power station. No one in the Western world has built one nuclear power station in that short a time. The Sikowski report said it would probably take 15 years to build one nuclear reactor in Australia. Third problem is economic. The Gen Cost study, recent experience in the US and Western Europe show that nuclear is much more expensive than solar or wind with storage. It's not clear that the community accepts nuclear power, and the 2007 experience underlines that when the Sikowski report said that Australia could build a nuclear power station if we were prepared to have a carbon price and other forms of subsidy. The Australia Institute did a desktop study of possible sites for the first Australian nuclear power station. And when it was released, the tsunami of panic among sitting members of Parliament had to be seen to be believed, as they all rushed to assure their community that it's not going to be at the Sunshine Coast, or it's not going to be on the Illawarra, or it's not going to be in Gippsland. And you might remember that when Mr. Crisafulli was bidding for your vote to be your Premier in October last year, he assured Queenslanders that a Crisafulli government would not accept a Dutton federal government imposing nuclear power stations on Queensland. Although he also said there'd be no new stadiums in Brisbane, so it's not clear how effective that assurance is. Final point is effectiveness. If we were to build 7 nuclear power stations in probably by 2037, that would produce about 5.5 gigawatts of electricity. 25 gigawatts of coal is due to be closed down by 2035. The current peak demand is about 40 gigawatts. The projected peak demand in 2035 is somewhere between 60 and over 100 gigawatts, depending on how rapidly we phase out petroleum-fueled transport and move to using electricity. But the lowest estimate I can find of the anticipated peak demand in 2035 is about 60 gigawatts. So even if we were to build 7 nuclear power stations, they would provide less than 10% of our needed electricity. Okay, so let me finally get to the issue of small modular reactors. The argument is that it would bring down costs and improve effectiveness if, rather than building nuclear power stations as a one-off operation on each site, we could have a factory production line producing the components which would then just be bolted together on the site. Standardised infrastructure, a relatively small footprint compared with an existing large nuclear power station. They would be expected to have passive cooling for safety. And remember, the problem with the Fukushima accident was that the tsunami knocked out the cooling system. They didn't have passive cooling. They required on water being pumped around. Without water being pumped around, the core melted down and it all went to custard. And the criterion for being called a small reactor is a capacity up to 300 megawatts. To put that in perspective, 300 megawatts would be a large solar farm or a large wind farm. Our small power stations have typically been 400 or 500 megawatts. The larger ones are about 1,600. Current status. SMRs are being developed in the US, in the UK, in Canada and Denmark. 14 individual designs are at a well-advanced development stage, but no full-scale prototype of any of them has yet been built. So the costs are highly speculative, and that's why the CSIRO estimate covered quite a wide range, about a factor of 3. Reasons for support. Well, the argument of those who are enthusiastic about small modular reactors, low carbon emissions. I mean, zero emissions is, to be frank, bullshit. And that's not just an issue about nuclear. It would be equally dishonest to say that wind turbines are zero emissions or solar panels are zero emissions. There is no zero emissions generating technology. To be equally fair, nuclear is low emissions, certainly low emissions compared with fossil fuels. The most credible estimates show it as about the same over a full life cycle as wind energy and a bit less than solar. So it's, it's a genuinely low emissions electricity source ranked with solar and wind. But it's more constant and reliable power. Sun doesn't always shine, the wind doesn't always blow, but a nuclear reactor is in principle available 24/7. Although in practice, I mean, the coalitions say that it would run for, a nuclear power station would run for 80 years and have a 90% capacity factor. No nuclear power station has yet run for more than 40 years, and the practical capacity factor in a country like the UK that's been running since the 1960s is 68% because of the time required to refuel and routine maintenance and so on. So it's not 24/7, 365 days a year power, but if you had a series of them, then you could rely on the fact that some would be operational at every given time. Third point is that electricity is not the only area we need to decarbonise. About 20% of our carbon dioxide emissions come from process heat, which mainly comes from burning gas. And a couple of the designs for small modular reactors, in principle, would be able to provide process heat as well as electricity. So that is an extra possible contribution. In principle, they could be faster to construct than large nuclear if there really was a production line producing the components, a significantly smaller footprint, and so they could contribute to energy security. 5 basic designs, and I'll just say a little bit about each one in turn. Boiling water reactor, high temperature gas-cooled reactor, molten salt reactor, pressurized water reactor, and sodium-cooled fast nuclear reactor. The simplest, boiling water reactor, being designed by GE Hitachi in the US. Steam is directly produced in the reactor vessel. In other words, the water that's used to cool it is also turned into steam to turn the turbine and produce electricity. So it's a single loop system. The coolant is the steam source. Very simple design. The idea of a gas-cooled reactor was being championed when I lived in the UK, and the argument for a gas-cooled reactor is that if you're using a liquid for cooling, if it gets hotter, the effectiveness of the coolant is diminished. Whereas if you're using gas as a coolant, if it gets hotter, the effectiveness of the gas of a coolant is enhanced. So in principle, gas-cooled reactors are intrinsically safer than water-cooled. The design of X-Energy uses helium as a coolant because it's inert and it doesn't absorb neutrons, and it would be operating at 750 Celsius, which means that it could provide process heat as well as electricity. Molten salt reactor has the radioactive material embedded in a molten salt, a fluoride or a chloride. So as a result, that also has a high operating temperature. There are 4 designs being developed in Canada, the UK, the US, and Denmark. Pressurized water reactor is basically a miniaturized form of the most common form of large nuclear power station. It uses pressurized water both as the neutron moderator and the coolant, and it has a two-loop system so that the coolant that is in the nuclear core transfers its heat to a secondary circuit of the water, which is then used to produce steam and turn the turbine. There are 5 different designs being developed, 2 in South Korea and 3 in the US. The NuScale system is an advance on an earlier design. NuScale actually is the only design that so far that has got an operating license. NuScale got an operating license from the US Nuclear Authority for their 53 megawatt design. They then decided to change it to a 70 megawatt design, and they got a commercial contract from the Idaho Electricity Authority, and they were contracted for a couple of years to supply small modular reactors to the Idaho Electricity Authority, but that contract was cancelled last year because the cost was ballooning and the Idaho people were unwilling to pay it. Finally, there are 3 groups all associated with GE Hitachi. An interesting fact about GE Hitachi, you probably know that General Electric was once one of the largest corporations in the US, but it went bankrupt building nuclear power stations. And it's now GE Hitachi because it was bailed out by the Japanese company. There are 3 designs being developed. I have to say I'm quietly terrified of the idea of liquid sodium as a coolant because it's a very dangerous material, and sodium combines explosively with water. So I wouldn't want to be living in the same state as a sodium-cooled fast reactor. But they say that if it could be made to work, it would provide high temperature heat as well as electricity. So a summary of the designs. Most of them are small, less than 100 megawatt. There's a few in the 1 to 200, 200 to 300, or greater than 300 range. So they're much smaller than any power station now operating in Australia. Potential markets, backup for electricity generation. Electricity generation now accounts for about 40% of our greenhouse gas emissions, and the other possible application is industrial process heat, which are 20% of our emissions. So what would be the steps to possible commercial release of a small modular reactor? First, the companies involved need to get a license to construct and finance to support building a prototype. And at the moment, they are not yet at that stage. They're still trying to get finance and a license to construct a prototype. So according to the Academy report, the most likely time when a full-scale prototype would be operating, perhaps early 2030s. The idea of a prototype is that you learn from it and you work out what's a commercially realistic design. Typically, there's a 3 to 5 year period from the prototype to being able to develop a commercial operation. And what the Academy report recommended is that if we were serious about buying small modular reactors, it would be sensible to wait until 2 or 3 designs were operating for long enough for there to be both confidence that they work and confidence in the figures for what the cost profile would be. So a realistic timescale, some full-scale prototypes could operate in the first half of the 2030s, commercial release sometime between the late 2030s and the mid-2040s, and the Academy report said, and I agree with this, the least risky option would be to consider adoption after designs have been successfully operated, rather than being the first out there with something that may not work. The other point I'd like to remind you of is that small modular reactors are only small compared with conventional reactors. The typical physical footprint, which is 10% or less than that of a standard nuclear reactor, is still somewhere between 2 and 6 football fields. And the smallest one of those 14 that I mentioned to you, the NuScale 77 megawatt reactor, the design weighs about 700 tons. So when I first heard about small modular reactors, I thought something would be in your garage or in a shipping container. They are only small compared with large nuclear reactors. They're not small in any normal sense of the word. Something taking up 2 football fields and weighing 700 tonnes is not small. 2 outliers. Rolls-Royce have a proposal that they're still trying to persuade the UK government to tip more money into, is a 470 megawatt small modular reactor. I mean, that's not a small reactor. The original Gladstone power station was about 450 megawatts. That's in Australian parlance, that's a significant size power station. So far, they've spent about $1 billion Australian dollars, and they hope that there'll be a prototype in the early 2030s. The other thing that should be added is that nuclear submarines have been running around now since the Americans launched USS Nautilus in about 1955, and they effectively have small reactors. And while nuclear submarines have been lost at sea, none of them have been lost because of a nuclear accident. They've been lost because of the other problems of operating submarine vehicles. I have to say, I've always been very nervous about the idea that you would put nuclear reactors in something that you know that people would try and destroy if there was ever a shooting war. And I haven't seen anything that convinces me that there wouldn't be appalling radiological consequences if a nuclear submarine was ever successfully attacked. That's another problem. So, what are the conclusions? Small modular reactors are almost certainly not operating in 2035. It's possible they'll make a small contribution in the 2040s. And I think they're more likely to be seen as an application for process heat than for electricity, because I haven't seen anything that convinces me that they can get anywhere near competing with solar and wind with storage for electricity. That would require both changing the laws, which currently prohibit nuclear reactors. It would require a new regulatory body, like the UK Office for Nuclear Regulation or Canada's Nuclear Safety Commission. In my first draft of this slide, I also included the US Nuclear Authority, but given what's happening in that society at the moment, I don't think anyone could regard their authority as a sound basis for regulating something as dangerous as nuclear power. Because of the timescale that would take to build and have functioning a reactor, there would have to be social license and bipartisan support. And I think you'd have to say at the moment, there's no evidence that there is that social license or bipartisan support. Finally, waste management is a significant issue for nuclear reactors. Generally, it's a particularly problematic issue for the small reactors in nuclear submarines because they use highly enriched fuel. And so there's a more complex and more intractable set of waste products than in the used fuel in a nuclear power station. Neither the US nor the UK, who've been operating nuclear submarines for more than 50 years, have yet figured out how to manage the waste from those small reactors. We have bravely agreed in the AUKUS deal that if the US gives us nuclear submarines, we will manage the waste at the end of their life. And somebody said it's a heroic demonstration of your faith in the technical ingenuity of future generations of Australians that we've agreed to solve a problem that neither the Americans nor the British have yet solved. Final point, I think Moya is right that the whole proposal is rather unsavoury, and I think Mr. Dutton is quietly hoping that people won't look into it too closely between now and the 3rd of May. That's all I want to say.